We found the capacitance of a parallel plate capacitor. It is epsilon 0 A by D, and we know how to increase capacitance. We must have large area for the plates, the conductors, and a very small gap. That small gap is a problem. Imagine two conductors, oppositely charged conductors, placed very, very close. Now the charge can jump through the gap, and also the plates would attract each other, so keeping them apart is a problem. Well, we could put an insulator in between the plates. That would solve the problem of keeping them apart, right? They would then, if it is a solid dielectric, non-conductor, it would keep the plates apart. Now you've learned earlier that the force between two charges decreases by a factor of k, where k is the dielectric constant, and so that's because the field in the dielectric will be k times less. So now if you fill the space between the parallel plates by a dielectric, the field becomes k times less, so the potential difference becomes k times less. So if potential difference becomes k times less, capacitance goes up k times. So the capacitance now will be k epsilon 0 A by D. This is when you fill the gap between the parallel plate capacitor completely with a dielectric. That's it. Well, now you would look for a material with a high dielectric constant, so that you can get a large capacitance with a very small gap. But let's learn a little about these dielectrics. This material, these dielectrics are basically, they have no free charges, no free electrons. Positive and negative charges are bound to each other very strongly. And sometimes the center of negative charge coincides with the positive charge, so there is no what you call dipole moment. Like you learned about magnetic dipoles earlier, south pole and north pole. Here it is positive and negative charge with, if there is separation, that's a dipole, but if there is symmetry in distribution of negative charge around the positive charge, then that will not have a dipole moment. Some molecules, on the other hand, have that asymmetry, and so the center of negative charge does not coincide with the positive charge, so they behave like dipoles. In most normal materials, these dipoles will be randomly oriented, so there is no net dipole moment. But then when you subject these dipoles to an electric field, well, say put them in a strong electric field, then these dipoles will orient themselves so that something like this happens, positive, negative, this way. Mind you, the negative charges experience a force in the direction opposite the field and positive in the direction of the field, so even if it were originally oriented in some direction, it will turn around. So this orientation leads to effectively an appearance of negative layer of charge here and a positive layer of charge here, and a field develops inside the dielectric because of this, a negative layer here, a positive layer here, so a field directed this way. This is the field in the dielectric due to the induced charges. So the net field becomes E minus EI, and that will be 1 by k times the external field. So this E minus EI will be E by k. That's what we learned about dielectrics. So the field becomes k times less, force between charges becomes k times less, where k is that dielectric constant. K is also called relative permittivity, and it's got a label like epsilon R, relative permittivity. So this is it. Let me elaborate on dielectric. It should be dielectric, like diamagnetism, dielectric. Dia means through. It's shortened as di, suggesting something like double, but no, dia, through. Well, basically there is electric field lines do not end up on the surface, they go through this material, that's why it's called dielectric. Well, just to know. Now, so this is what you need to know. Well, why does a dielectric cause the field to become k times less? There will be induced due to the reorientation of dipoles, there will be field directly opposite the external field, and so you'll have field k times less. So that's it. Well, if you have, and one more thing to know about the dielectric is that it's not like you can have a very strong field here. If the field is very strong, then the positive negative charge which experience force in opposite direction can break apart. So the dielectric can become a conductor. So they have a breakdown field strength, let's say EM. So this is the maximum field strength that dielectric material can withstand. Above that becomes a conductor. So when you have a dielectric, there is a limit to the maximum potential difference you can have between the plates. That will be EM into D, right? That's VM. The maximum potential difference will be EM into D. Remembering that energy stored depends on V, right? So if V cannot be very large, then we'll also have we can't store too much of energy in the capacitor. Capacitor not known store too much of energy anyway, but this also is a limitation. The dielectric can become a conductor, breakdown, so the charge wouldn't stay on the plates. The dielectric acts as a leak. So that's what happens. So how do you make a very good capacitor? Well, large surface area, small gap, a very good dielectric with high breakdown field strength, right? That would give us a good capacitor. Here we have something called a supercapacitor. Its capacitance is 500 farads. Its breakdown voltage is 2.7 volt only. So this is really a large capacitor, 500 farads. And imagine large. Remember, for Earth it was some 700 microfarads. This is 500 farads. It's like a supercapacitor. Now, how do they make those supercapacitors? Well, imagine having a thin metal foil and a thin dielectric, another thin metal foil. We don't need a thick metal plate. We don't need anything strong there. We need just a layer, a surface for charges to stay, right? Charges stay on the surface of metal, right? So we don't need thick metal plates there. So thin foil is good enough. Then you can put another thin foil here, non-conducting foil dielectric, and then roll. So that will give you a fairly, in a small compact space, you will get fairly large capacitance. So a very good dielectric, very small gap, because we are basically using foils there, thin foils. So you get a large capacitance. So nice to have a capacitor like that. Well, but then you can see if you use a good dielectric and make the gap small, you cannot have a large value for VM, so you cannot store a lot of electrical energy. Half CV squared is the energy stored, right? We found that energy stored is half CV squared. Well, if V has a limit, then you cannot store a lot of energy. Well, if you want to increase C, you must decrease the gap, and if we decrease the gap, well, V decreases, the maximum value of V decreases, so that's a limitation. Anyways, that's about parallel plate capacitor and the action of a dielectric. Simple thing here that's happening is the field in the dielectric is k times less compared to the field outside, so the potential difference between the conductors decreases by a factor of k, capacitance goes up by a factor of k. You can replace it by epsilon r if you like.